Okay, so welcome everyone to Lecture 6. So a few things you may have noticed, I reorganized the topics of the course a little bit. So originally we're going to talk about greedy algorithms today, but because the exam is going to be on Monday, I thought it'd be weird to just kind of do a completely different topic. So we're going to talk about graph algorithms today. And the reason why we're doing this is because a lot of graph algorithms is like dynamic programming. So hopefully you'll get a bit more review about dynamic programming before the exam. Also, homework 3 is due Friday. I hope everyone's looked at it. It's mostly just covering dynamic programming and should be good review before the exam. The midterm's Monday. If you didn't see, there's a Piazza post that asks some questions about the midterm, and I have my answers there. And I'm going to send out a Piazza post with the formal stuff, but the exam, it's going to be 2 hours. It's going to be during class. So it's 2 hours during class time. It's going to be covering DP and recursion, basically everything we've covered up to this point. And yeah, so for other things about the midterm, you can ask, or I'll post on Piazza. Yes?
Other than their connection to DP or graph algorithms, should be on it?
Yes, so we've been covering graph algorithms the entire semester, like implicitly. This lecture is mostly like review. I don't think, I mean, assuming you've taken 240 and like 400, you've probably seen, we're gonna talk about like DFS and stuff, so it's nothing super intense other than the DP parts. Other questions? Okay, so I also put up here the readings that you should have completed by now. And so particular, all of chapter 0, almost all of chapter 1, so that's the recursion stuff, chapter 2 backtracking, chapter 3 DP, and then chapter 5, which are the basic graph algorithms, except for 5.7. So 5.7 are graph reductions, which are like, in my opinion, the most general technique in the entire course, but it's really wacky. It's really weird. So I didn't want to spring that on you guys right now. So we're gonna save that for 2 weeks from now. So you can skip that last chapter in 5. But I highly recommend you read through all of these and try some of the textbook problems, because I'm mostly using the textbook problems to make the exam. So if you solved all the textbook problems, I can almost guarantee you'll get 100 on the exam, almost. But if you can solve all the textbook problems, you shouldn't be in the class anyway, because that's really impressive. Okay. So I also thought I'd give you just a couple buzzwords to help you remember these things. So let me just throw in a new page. You always want to kind of keep these phrases in mind because they're kind of important for the course. So again, the key ideas, there's reductions. This is using other problem solutions to solve your problem. It's the most general technique in the course. It's very intuitive. Every time you call any standard library in code, you're implicitly doing a reduction because you didn't write that code. You're assuming it works. You're not looking inside the code to check it works. You just use it and assume it runs well. In everyday life, you reduce things, your route to get from one city to the other. You use Google Maps. You don't really think about how Google Maps works. You just trust it. And then a specific type of reduction is recursion. And this is specifically when you recurse or you reduce to the same problem that you're trying to solve, but of smaller size. Or you could think of it as you have the magical recursion fairy who can solve the problem for you if it's smaller. otherwise known as the recursion theory, otherwise known as the induction hypothesis. So another thing that goes with this is induction equals recursion. They're the same thing basically. And induction is our friend. So that's another key thing. What's divide and conquer? That's just a different kind of recursion. Almost all of these ideas are just recursion, but applied differently. So divide and conquer is recursion, where the subproblems are significantly smaller. So in particular, you could think of n over 2, n over 3, some constant fraction. Whereas in contrast, if you remember the pancake problem, and Tower of Hanoi, we reduced those to problems of size n minus 1. We only made a little bit of progress each time. For divide and conquer algorithms like merge sort, you're cutting the entire input in half. So you're making a significant amount of progress at each point in time. And so usually these algorithms are much more efficient than just straight up recursion, but they're also harder to come up with. Okay, the next one's called backtracking. So backtracking is a little weird because it's the one you're using most of the time, but we don't really acknowledge it. So backtracking is just recursive brute force. So the key phrase here is try them all. And the weird part is backtracking is what you're doing in every dynamic programming algorithm. So this is a part of dynamic programming. So that's why you probably don't really think of it. Then dynamic programming, this is just backtracking usually, but we're going to call this recursion without repetition. So the main difference here between dynamic programming and backtracking is every dynamic programming algorithm is usually a backtracking algorithm, but not every backtracking algorithm can be made into dynamic programming. So it only goes one way. The reason for this is, like we saw with the n-queens problem, sometimes the reason your problem is hard is not because you're repeating the same problem over and over, but just because there's just a lot of subproblems. So for n-queens, you had to remember every possible previous queen, so you get this exponential tree of possibilities. So these just might have too many subproblems. And so no matter what you do, it's going to be slow. Whereas the key thing for dynamic programming is there's not a lot of subproblems. They're just repeated a lot. So there's few unique subproblems. They just would be called several times by the recursion. So let me make this. And so basically, we can make it efficient by memorizing those subproblems. That way we're not repeating them. But for general backtracking like n-queens, even if we memorized everything, if you're not repeating them, you're not saving any time. You've just stored things for no reason. So that's the critical difference here. Dynamic programming algorithms are backtracking. So backtracking is important. But you're typically never explicitly just doing backtracking. Because if you were just doing backtracking, you're probably solving an exponentially hard problem. So you probably shouldn't be solving it. You should be tweaking the problem slightly to make it easier. But we'll talk more about that at the end of the course. But yes.
Why do we call it backtracking? Why not like brute force or something?
So ideally, it's recursive brute force. That's what you want to remember. The reason it's called backtracking is because if you look at how the problems are solved, you start by solving the problems at the leaves of the tree. and you use that to push answers up to the top. So if you looked at the recursion tree, the way it's actually evaluated is at the bottom first. It's a bottom-up algorithm instead of top-down. So that's why it's called backtracking, but the name's not important. Just remember recursive brute force, because you're going to brute force, try every possibility of something, and then recursively solve the rest of the problem, given those choices are fixed.
So all recursive algorithms are backtracking as well?
All backtracking algorithms are recursive.
But not vice versa?
Yeah, it doesn't have to be. So backtracking specifically has the connotation of the brute force part. Essentially, every recursive algorithm does start at the leaves. That's pretty much true. But the names are used for more specific things. But again, don't get caught up with the names. I mean, I'm not going to be on the exam and be like, what's backtracking mean? I'm just letting you know this so that when you're reading the textbook chapters and you're like, I don't remember us talking about backtracking, I don't want that to dissuade you from actually reading that chapter, because it is important. We just don't really explicitly talk about backtracking. But it's always there when we're doing DP, implicitly. So other questions of what we've done up to this point? So the most important one is reductions. I keep emphasizing this because we're not always directly using reductions. Usually it's kind of implicit. So recursive algorithms are reductions of a certain type, but they're not the most general type. So if you guys saw the homework 2 solutions, the easy way to solve the last problem was using a reduction to the maximum independent set problem, because they're the same problem. So that's implicitly a reduction. If you haven't seen that, you should check it out, because there's going to be a couple homework problems like that where there's hack solutions that make your life easy if you use a reduction. Okay. And so today we're going to talk about maybe all this stuff. We'll see. The basic graph theory stuff will just be review. It's going to be really boring, but I'll try to make it quick. So if you have questions, make sure you stop me, because I'm going to just roll through all of that really fast. Then we'll talk about DFS. The main thing is this idea right here, topological sort. But everything else should be mostly familiar to you. So any questions before we get into graph theory? Okay. Graph theory. What's a graph? This is a graph. Now you're all experts in graph theory. So graphs typically are represented as these diagrams of circles with edges between them. Ultimately, what a graph is doing is it's modeling a binary relation. So what's a binary relation? It's just a set of pairs. So it's some set of AB such that AB satisfies some property. You could think of this as less than or equal to. So A is less than or equal to B. That's a binary relation. A equals B, that's a binary relation. And all of these are defining a set of pairs, right? You have the set of pairs AB for which A is less than or equal to B. And you can model any kind of binary relation using a graph. So the idea here is each object, the A and B, become a circle in your picture. And then you put an edge between them, which is a line connecting them, if the predicate P of AB is true. So if you had a less than or equal to graph over the integers, it would look something like this, where you have 1 is less than or equal to 2. So let's draw it like a directed graph. So this is saying that 2 is at least 1, 3 is at least 2, and because it's transitive, we also get this other edge, 3 is at least 1. But it is not true that 1 is at least 2, and so we don't have an edge there. If we want to be really specific, 1 is at least 1, and so we have these self-loops too. And so that would model the less than or equal to operation on the first 3 integers. And in general, it doesn't have to be something so mathematically defined like less than or equal to. It could be anything. So an edge could be you can make it from city A to city B in less than 10 minutes. It could just be there exists a road from city A to city B. These edges can model pretty much anything. And so that's why graph theory is really powerful, but also really confusing because it has so much expressive power. You can model almost anything as a graph if you really tried. Now the key restriction here is graphs are binary relationships, but there's things called hypergraphs where you could have arbitrary relationships. You could have groups of 3, groups of 10, whatever. And so if you include hypergraphs, then you get pretty much anything you could ever imagine ever. So it's very, very powerful. But the main takeaway, the main thing you need to remember is just models pairs of things. These edges are just pairs of things that we care about. You could think of a social network, and these are friendships. So each edge means you're friends with the person on the other side of the edge, stuff like that. Another example is a tree. So a tree formally is a connected acyclic graph. Connected means it's connected. I think that's obvious. Acyclic means there's no cycles. So there's nothing like this in your graph. An example, the classic example is a family tree. You have the root, which is your primary ancestors, and then they had children, and those children also had descendants. And it's called a tree because there's no cycles, right? You can't be your own grandfather, hopefully. So that's a tree. These are the main high-level ideas. Any questions about the high-level idea before I throw like a ton of math at you? Okay. So right away, I'm just going to give you this message. There's a bunch of data structures to represent graphs. We'll talk about a couple. But no matter what, always assume the graph is represented as an adjacency list. We're not going to be using the adjacency matrix usually. We're not going to be using the other Fibonacci heap implementations of adjacency list. Just assume a basic adjacency list, like a single linked list that you've seen in like CS300. So when in doubt, just it's an adjacency list. Won't really affect anything because you're usually not even going to think about the data structure. You just think about the pairs. Okay. So we're going to go to the textbook for a bit just because there's like 1,000 pictures. There's no way I was going to copy them all. So here's some example of graphs, very, very old graphs. Nodes and edges, really cool. This one's representing physics equilibria, which is kind of also super cool. They even drew like little balloons on there. A lot of cool pictures. So here's all the definitions. So what's a graph? A graph is a pair, V and E. V and E are both sets. E is a subset of V cross V. So edges are always pairs of vertices. And in particular, because this is a set, you can't have duplicates. So if you have the pair UV, it can only appear once in your graph. You can't have UV like a bunch of duplicates. And these are called edges. The vertices, which are the elements of V, these are called nodes, or you could call them vertices. Either one's fine. So edges are just pairs for an undirected graph. So there's two types of graphs that we'll care about. There's directed and undirected. Undirected graphs are just, they satisfy the symmetry property. So if UV is an edge, that happens exactly when VU is an edge. So you could think of it as has arrows in both directions if you want, or you can just think of them as directionless. And because it's a set, right, the set UV is equal to the set VU. They're the same in terms of sets. And so that's another reason why they're implicitly in the edge set. For a directed graph, they aren't subsets, they're pairs, UV. And so the pair UV does not necessarily equal the pair VU. So you could separately in a directed graph have two edges, like a little cycle, whereas for an undirected graph, it would just look like that. There's no arrows going both ways. So that's what edges are. That's how they're represented in both cases. In general, V and E will denote the number of vertices and edges in the graph in addition to just being the sets. It's slightly confusing, but you'll know the difference because one will have a big O usually, and that's how you know it's referring to the number. So for edges, there's endpoints. So UV, U and V are both the endpoints of the edge UV. For a directed edge, U to V, like this one here, then we call U the tail. It's the one without the arrow, and we call V the head. So the head is where the arrow is pointing to when you have a directed edge. Okay, in general, these are all examples of simple graphs. So what's a simple graph? They don't have self-loops, and they don't have multiple edges between them. So as I mentioned, there's other types of graphs. So for example here, there's 3 copies of the edge UV. That's called a multigraph. In a simple graph, we don't allow that. Between any 2 pairs of nodes, there can be at most 1 edge in a simple graph. And we're pretty much always going to talk about simple graphs. In general, when you have a simple graph, if you can solve a problem for simple graphs, that usually immediately extends to multigraphs because you just replace the single edge with many and really doesn't affect much. So we won't really talk about multigraphs or hypergraphs. So for the most part, you can assume things are simple graphs if they're undirected. So for directed graphs, there's not really the same notion of simple because for a directed graph, you can always have a self-loop. That's fine. For a normal graph, an undirected graph, the issue with self-loops is it's a set, right? So if you have the set VV representing a self-loop, that's not really, that doesn't exist. This is just a single set with a V in it. So if the edges are strictly pairs of things, or 2 subsets, a subset of size 2, then that can't really exist because it's not size 2. So that's why you have to slightly tweak the definition of graph to get self-loops. But for directed graphs, they're pairs. And the pair VV is a valid pair of size 2. So you can have self-loops in a directed graph, but not in a simple undirected graph. Okay, so next thing we care about are neighbors. So what does that mean? So for an undirected graph, U is a neighbor of V if there is an edge between U and V. So if U and V have an edge, V is a neighbor of U, and the neighborhood of U is the set of all things with edges to U. So this whole thing is the neighborhood of U. And we say that U and V are adjacent if there's an edge between them. There's all kinds of words that mean that. You also say V and U are incident. You'll just see a lot of words that mean the same thing, that there's an edge in the graph. Now, the degree of a node is just the size of the neighborhood. It's the number of edges that leave U for a undirected graph. For a directed graph, that's not as defined, so we need to talk about in degree versus out degree separately. So in degree is the number of things with arrows pointing to you. So it's the number of these in arrows, whereas the out degree is the number of out arrows. And an edge u to v, for any such edge, we say that u is the predecessor of v and v is the successor. Okay. Next thing, subgraphs. This one's really easy. You just take any graph and you delete nodes and edges. So you can delete an edge and it's a subgraph. Now if you delete a node, you have to delete all the edges touching the node as well. That's the only special part. So that whole thing is a subgraph of the original graph. So just any graph with the vertex set being a subset of the other vertex set and the edge set being a subset of the other edge set. Now, a subgraph of a graph could be itself. So there's two trivial subgraphs, the empty graph and the graph itself. These both count as subsets of G. And so we typically talk about proper subgraphs. This is just any subgraph of G other than G itself. It's proper because they're different. Okay, so those are just words. Now we're going to talk about concepts. So what's a walk in a graph? Well, it's just some sequence of edges. Or you could think a sequence of vertices. So you have U0, U1, U0, U1, U2, up to UK for some K. And the stipulation here is for each pair, the edge U0, U1 needs to be in the graph, and in general, the UI plus 1 needs to be an edge in the graph too. So a walk, intuitively, you probably heard this being called paths before. It's not actually called paths, but just sequences of nodes in your graph that you follow. So maybe you start here, you take this edge, you take that edge, this edge, this edge. You can go back. You could follow around the loop a couple times if you want. Just keep going around and around. And then maybe you go back to where you started. So that's a walk. You're just walking through the graph, following edges as you go. Okay? So that's what a walk is. Now a walk is called a path if each vertex is visited at most once. So in other words, there's no repeats. So if there's no repeats, it's a path. So if we change that example there to be this one, so same graph, but now we're going to just do this. That's a path. So we never repeated a vertex. The second we take one more edge, it's no longer a path. It just becomes a general walk then. Okay. Then a vertex V is reachable from another vertex U if there exists a path or exists a walk from U to V. So in particular, if there exists a walk, there also exists a path. So if there exists a walk from U to V, that implies there exists a path. Does everyone see why that is? I'll take that as a no. So if you haven't seen this before, this is a classic proof by induction. So, yes.
Is this only for undirected graphs?
Yeah, we're looking only at undirected graphs. Yep. Yes.
You said it's only reachable from U to V if there exists a path.
Yep. Technically, there exists a walk, but what I'm going to prove right here is that if there's a walk, there's also a path. So they're equivalent. So let's just think of a general walk from U to V. So here's a walk. If it's a path, we're done. So if it's not a path, we must have revisited some node. So there's some middle node W that got revisited. So really, the walk looks like this. Now we're going to do this by induction on the shortest path length from U to V. So in particular, this walk has some length. And for any smaller length walk, we can get a path. So notice that this walk from U to V that takes this detour in W, well, we can just kill the detour, right? We kill that detour, and then this blue path that just skips the detour is shorter length than the original UV walk. So the induction hypothesis implies there exists a path inside that single blue line there. And so that path is the path from U to V. The base case is if you start at U, there's a walk of length 0 that does nothing. Walks of length 0 that do nothing are also paths because they don't revisit vertices. It doesn't visit any vertex other than U. Similarly, if you had a single edge, if you also want to do the base case when there's one edge, obviously, again, any walk from U to V that doesn't go back to U is also a path. So let me make this undirected. So you can go from U to V in just one step, and that's a path. You didn't revisit anything. Okay, any questions on this induction proof? Yes?
Can there be cases where there are walks?
Nope, that's a proof of why not.
For example, 5 nodes,
Mm-hmm.
and the second and fourth node has node sticky on it.
So 5 nodes, and then
Second and fourth node has a node that doesn't, each has a node that doesn't connect.
so like this.
Yes. There would be a walk that would have. Oh, it doesn't have to include every node.
Nope. It just has to follow edges till it hits V, the end. And so if the original walk did go up this hill, it can just be like, we're not going to do that anymore. So that would be our W up here. You can simply just choose to ignore that part. And so once again, the recursion fairy / induction hypothesis can correctly give us a subpath in the part without the loop. Okay? So if you're not super comfy with these kinds of induction proofs, you might want to practice them because we're going to take this kind of thing for granted like at least 30 times that I can think of right now. Like actually 30, I'm not even exaggerating that number. So you want to be able to do these kinds of proofs in your head like instantly, basically, for these really simple concepts. Because once you're doing more advanced stuff with graphs, you're going to want to be able to have induction in your arsenal. Yes?
What was your inductive hypothesis?
My induction hypothesis is for any walk of length less than W. For any, bigger, for any walk of length less than W, there exists a U to V path in the walk, or as a subset of the walk. So by subset of the walk, I mean literally you delete some of the edges, that's all. And if you unroll this induction proof, what it comes down to is you have a bunch of edges, U0, U1, etc. And you're just, really this is an algorithm too. You're recursively picking edges to remove such that the overall walk isn't really affected. So if we looked at the picture here, we went through, we found this W that didn't really add anything to our walk, and we removed it. We killed all of those edges in a row. Then we're kind of recursively doing the same thing. We find another vertex that has like a little loop, and we also just remove those from our walk. And so the sequence of vertices we have is shrinking and shrinking until eventually the only way to shrink it more would to be remove an essential edge that would make the walk no longer connected. So at the very, very bottom of this recursion tree, the last thing that would happen is this edge is considered for removal. But if we did remove it, then U and V would be disconnected. So if we remove that, then U no longer connected. Because there's a critical edge missing. So that's at the very bottom of the induction proof. And so once again, induction is recursion. This induction proof that relied on the recursion fairy or induction hypothesis to give us the smaller path is also a recursive algorithm. You find any node that has this extra loop. So you find any node that's repeated in your walk and just kill everything between it. And recursively, you're continuing the process on the smaller and smaller walk until eventually the walk is just a path because there's no more repeats. Cool. Any other questions about that? Awesome. That was a good example. Okay, so reachability is equivalent to there's a path from U to V in the graph. Then we say the graph is connected if every single vertex is reachable from all the others. So pictorially, this is really natural. It just says the graph looks like this. There's no nodes over here. This can't happen because there's no way to reach those nodes from those up there. There's no edges connecting these two components. Okay? But whenever a graph is disconnected, you can break it into components. So components are just the maximal chunks of connectedness in a graph. So this would not be a component because you can make it larger. So as long as you can keep adding nodes without it becoming disconnected, you have to do that. So this whole thing is a component because if we try to add anything else, it's disconnected. Anything else you try to add will disconnect the graph. You no longer have reachability. But each of these individually is connected. So these are the two components of the graph.
But we define graphs in terms of relationships, right?
Mm-hmm.
If we have two disconnected like graphs, how they connect, like what's the relationship between them? There's no relationship, right?
There's still relationships. So think of this as like a road network. If you have a map of city connections, you could say this is Tokyo and this is Madison. Then, there's no roads from Madison to Tokyo because of the ocean, but you still would want to have that information in your graph because it's just about road networks in general.
Even if there's like a separate node sticking out.
Yep. So it just depends on the context, what properties you're looking at. So for road networks, you would want to consider these all separately. For a family tree, then it wouldn't make sense to have like off branches. Because the whole point of you looking at a family tree is to analyze a single family. So it just depends on what you're trying to analyze. Okay, so we're almost done. A walk is closed if it ends at the same vertex. So that would just mean something like this. This is our walk. So we started and ended at the same vertex. A cycle is a closed walk that doesn't repeat any vertices. So you could think of it as the closed version of a path. So this one is a cycle, because the only vertex we repeat is the one we started at. So that's what a cycle is. A graph is acyclic if it has no cycle. In other words, it has no closed walks either that can avoid, that don't use the same node more than once. Acyclic graphs are called forests in general, but as I said before, if it's also connected, then it's a tree. So a forest is just a bunch of trees, just like the actual word forest means. So you have a bunch of trees. They're all separate, though. So in the picture, you would have something like this. This is a tree. Now this is a forest, because you have two trees that are not touching. Now if you connected this tree to that one by making it part of a leaf, now it's a single tree instead of a forest. So this is a tree, not a forest. Okay. And so always trees are a single component of forests by definition. And the last thing we care about are called spanning trees. So a spanning tree would be if we took a graph, let's say this one right here. So a spanning tree is just a tree subgraph that touches every node. So here in this picture, the spanning tree are these red edges. It's a tree. It doesn't have any cycles. And it's touching every single node, and it's connected. So it's a connected acyclic graph, subgraph specifically. So it's connected, it's acyclic, and it's a subgraph of our graph G. And so it's called a spanning tree. So the reason it's called spanning is because it spans the whole graph. So the spanning part means touches every node. So span is not a concept exclusive to trees. You can have general spanning subgraphs. So if we also added these two edges, or that edge in, well, we just get the whole graph back. The whole graph is a subgraph of itself that touches every node. So the graph itself is also a spanning subgraph. And then similarly, you can have a spanning forest. Same thing, but instead of a single tree, you have a bunch of them because your graph is disconnected. Okay, and then the last thing is for directed graphs. All the stuff we just talked about is slightly different. So now you have a directed walk. The difference for directed walks is just instead of a pair UI plus 1 being an edge, you need the directed edge, so you're going in the right direction. So in particular, in a directed walk, you can't go this way because there's no edge going that way. That's the only caveat. Reachability is different, so reachability now is about directed walks instead of just undirected walks. So one cool thing about normal graphs is if U is reachable from V, that implies V is reachable from U. Why is that? So what does it mean for U to be reachable from V? Yes, I saw finger gestures. That's correct. So that means there's a walk from V to U. So we have this walk here from V to U. Now, can we get a walk from U to V from this? Yeah, so we just take the same sequence and flip it. We just follow the walk in the opposite direction. But for directed walks, we can't do that because the edges always go in a specific orientation. They're going in a certain direction. So if we have this walk from V to U, that doesn't mean we have a walk from U to V anymore. It's not symmetric. And so in general, it's harder to find components in a directed graph. So a component in a directed graph is called a strongly connected component. And this means for every pair V and U, there's a walk in both directions. So you can get from V to U, and you can get from U to V. Both of those walks need to exist. And so finding strongly connected components is a bit harder to do than for a normal graph. But we'll come back to that later. And then similarly, a directed graph is a cyclic if it has no directed cycle. And a directed cycle is exactly as you'd imagine. It's a cycle, but now it goes in order of the edges. Okay. Any questions on all these definitions? We've gotten through all the definitions. Let's look at some examples. So generally, when you're looking at a graph, like I said, it's just a set of pairs or set of subsets of size 2, depending on if you're looking at directed or undirected graphs. But usually you want to draw them, and here's some drawings of graphs. So a drawing is just literally you're on the plane, a 2D piece of paper, and you draw circles with the lines connecting the circles if there's an edge between them. This is usually how you see graphs, pretty common. Now, a graph is planar if you can do this without edges touching. So notice here, none of these edges are crossing each other. There's no crosses. But on the other side, notice here there are some crossings right here. All these edges cross each other. And so this graph is not planar. But this one is planar. Okay? Planar graphs are really useful graphs. Any kind of map, like a physical map, is planar, or you can make them planar at least. And planar graphs are nice because you can typically solve problems on planar graphs more efficiently than normal graphs. But we'll talk about that later. For now, just look at the picture. We have pictures of graphs. That's what you're typically going to see. So if we had some underlying property that defined the graph, then we can explicitly mention it. So we know that P of AE is true if P is the underlying predicate that defines the pairs, because A is connected to E in the drawing. So these two things are equivalent, the physical edge being drawn and this predicate being true. Here's more examples. So if you considered a bunch of line segments right here and looked at where they intersect physically in the plane, well, then you can model that by this graph, actually. So this graph is actually modeling the intersections between the line segments. And similarly, if you looked at the intersections of all these circles, and you made each circle a node, and the edges mean these are intersecting, then you get the same graph, actually. So this graph is modeling the underlying predicate that says both these objects are intersecting or not. Another important example, which is more important for us, is dependency graphs. So these you've been drawing for homework and for DP. The dependency graph is usually when I draw the big square, and we have ij, and we draw arrows from other ones. You know, I use squares for that, but if you just made them circles, it's a graph now. And so all this time, you've actually been drawing dependency graphs. You just didn't even know it. So for the Fibonacci sequence, we actually have this dependency graph. So it means that one subproblem has an arrow to another if that subproblem is needed for the other subproblem. So in particular, the subproblem f of 2, to compute f of 2, you need f of 1 and f of 0. And so you have these directed edges from 0 and 1 into 2. And similarly, you can continue this. So if you looked at 6, to compute f of 6, you need f of 5 and f of 4. And so you have arrows coming in from f of 5 and f of 4. Okay? Now notice this is different from the recursion tree. So the recursion tree models what's actually called. So it might have repeats, right? But the dependency graph just says what is needed. Okay? So you can think of the recursion tree as the backtracking tree. This is if you don't use DP and just leave it as is, you get this tree. But the dependency graph is if you include memoization. So if you include saving things so there's no repeats, this is the graph you would get. So this is the DP tree when you use the memoization. That's one way you can think of it, or just think of it as it shows you the dependency between subproblems. So any question on the dependency graph? Here's another example. So at a distance, I did in a video. It's really intense because this is the dependency graph. So for any ij, so let's pick an ij. So for any ij, you have dependencies on the thing that comes to the thing that's right above it, the thing to its left, and the diagonal above it. So in this picture, you have, here's the thing above it, here's the thing to the left, here's the thing at the diagonal, and you'll notice they all have arrows touching it. So here's another example of a dependency graph. Again, modeling which subproblems depend on which other subproblems. There's also this idea of a configuration graph. Again, this is when you're looking at game trees. So remember we looked at game trees where you have a state. States model like a current board position. So it's some current board. So in tic-tac-toe, maybe there's like 1x. And then you have edges to every other state that you could enter next. So maybe the next player puts an O there, the next player could put an O somewhere else, etc. So it's modeling all the moves that could be made and the valid board state in the next round after that move is made. So a configuration graph is basically modeling the gameplay dynamics. And this is slightly different from a game tree. Why is that? Because in an actual game tree, you might repeat the same board configuration multiple times. So if you're playing chess, if you just had 2 pieces, you could just keep moving in circles and eventually you reach the same state again. But in the configuration graph, that wouldn't happen because it's just modeling valid moves overall. It's not an actual game play. It's just what states are possible and what connects them. There's no actual players playing them. So you'll never have any moves like that. And here's the actual picture for the Tower of Hanoi, if you consider that a game. So this is the actual tree. I kind of checked it, and I kind of went crazy checking it. So this top node is when you have everything on one peg. If you look at this random node over here, that's a specific configuration where you have that situation. And then over at the bottom right, this is the final solution that you want. The bottom left is also a solution, but instead you've moved them to the middle peg instead of the rightmost peg. So that's another example of some graphs. Okay, so how do we represent graphs? Well, I already told you we're always going to use the adjacency list. So what's an adjacency list? It's this thing right here. It's an array where every node is an element of the array. So these are all the nodes. Typically, you want to first convert the nodes into numbers. So for example here, there's an implicit labeling function, L, that maps a node, A, to 0. And in general, it's going to take a letter, alpha, and it's going to output the distance from alpha to A in the alphabet. So B is going to be number 1, it's the second thing in the array, and so on. So in general, nodes can be whatever you want, right? They could be circles in the case of the intersection graph. They can be restaurants. They could be anything you could imagine. But when you put them into a computer, you need some representation. So typically, you're going to choose a labeling function or a way to convert your actual nodes into some representation here. Usually, it'll just be integers, right, from 0 to whatever, because that's what indexes the array. So once you have that representation, then all an adjacency list does is has a literal linked list that specifies every edge. So if you're in the A element of the array, you're going to have a linked list of other nodes, and this represents the edges. So an edge AB exists in the graph because B is in the edge list for A, or also called the adjacency list. So that's why it's called an adjacency list. It says these nodes right here are all adjacent to A, and they are. So just a literal list storing what things touch A, and you do this for every single node. Okay. So important things about the adjacency list. There's certain operations it supports. So you can check whether an edge exists. How do you do that? So let's say I told you, tell me if UV exists. We're going to go into the U or V, whichever you prefer, element of the array. And you're just going to do a direct scan of every element in that linked list and see if V is in there. If V is in there, then you know the edge exists and you're done. Otherwise, you know it doesn't exist. And this is specifically for undirected graphs. Okay? So what's the running time of this operation? In the worst case, it's 1 plus the degree of U. That's because we have to check, in the worst case, if V is not in there, we have to check every single thing in this list. And the length of that list, by definition, is the number of neighbors, which is the degree of U. So that's how long it takes. Okay, other things you can do, besides just check if an edge exists, is you can insert an edge. You can delete edges by just doing linked list stuff. And those are all things, you could do. And they're all going to take around the same time, 1 plus the degree of U, because each time you're going through the entire adjacency list for that node, and then plugging something in, deleting something, whatever you want to do.
We first have to find U as well, so shouldn't that be like degree, like order of U plus degree?
We're assuming you can index into the array instantly. So that's why it's just a 1 here. In general, yeah, you're right. So when you're actually scanning memory, sometimes it takes longer to hit like the end of the list, the end of the array. But for this class, we're going to assume like all basic array operations are constant. It's truly random access. You can actually physically just jump to wherever you want instantly. So this is the key running time you want to care about. So in general, if you're going to search a whole graph, if you look at every node and edge, the running time is going to be O of V plus E, because the running time is going to be a sum over all U of 1 plus the degree of U, because that's the time it takes to do something in the adjacency list. But if you know from graph theory, the sum of the degrees, that's exactly going to be, so we just take the 1 out, that's just going to be a sum of all U, so that's the size of V. And the sum of the degrees is exactly 2 times the number of edges. So you have the number of vertices plus twice the number of edges, so O of V plus E. So that's what you really need to know. If you're going to search through an entire graph, you're looking at all the edges, looking at all the nodes. In total, you're doing O of V plus E work. So you don't even really need to remember that each individual one does degree of U. You just need to remember that overall, that's how much work you'll be doing. So that's the key thing there. Okay? So if you've never seen this before, the sum of the degrees is 2 times the edge list. It's called the handshake lemma. It's a really nice discrete math proof, so please look at it if you're not familiar. There's also adjacency matrices. These are even easier. So an adjacency matrix literally just has every pair in a matrix, and it says 0 if that's an edge, and 1 if it's not. That's backwards. 1 if it's an edge, and 0 if it's not an edge. So notice A has no edge. There's no self loop, so that's 0. But AB, there is an edge between A and B, and so that's 1 right there. This is pretty standard. We won't be using it much. Again, you can always assume that we're going to use the adjacency list. And here's a huge comparison about all the operations and how fast they are if you care about data structures. Again, for all of these, the difference is on small scale versus large scale. So if you're searching the entire graph, they're all going to take V plus E time. But if you just search a single thing, like if you just check a single edge, is there or not, some of these can be faster than others. But we typically won't be doing that, and so you don't really have to worry about this chart too much unless you're interested. So yep, those are basically all the data structures. So any questions about that? This is the main thing. Yes?
So adjacency list does not reflect the most efficient data structure. So do we use it like it makes our job easy, like it makes parsing graphs easy?
Yeah, so that is, so Jeff actually talks about this. So the reason we use adjacency lists is typically because they are the simplest one, but also they're good enough. So like I said before, on the small scale, an individual operation could be slower than if you used like a hash table or something fancy. But if you're doing a lot of operations, overall they're roughly the same time anyway, and these are usually simple. So that's one reason why you would prefer to use an adjacency list, is the simplicity. But the main reason is this one. So you're not always looking at graphs as modeling mathematical things like the chart I showed with 1, 2, and 3. Usually you're modeling very complex relationships, like social interactions between humans, for example, or some other mathematical quantity that has some representation. So if you want to use the more complicated data structures, like I said, you have to convert whatever thing you're looking at into a graph first. But if you just use adjacency lists, you don't physically have to do that. So most things, if they model pairs in some way, you can just use their pair operation. So whatever objects you're looking at, I mean, the whole reason you're modeling them as a graph is because they support some kind of pair operation. You can check if two things are related in some amount of time. So if I gave you that natural representation, if I gave you in Java the social network, not a graph, but a social network object, and I said run a graph algorithm on it, you don't actually have to physically convert it into a graph. You can just use the pair operation every time you have to check for an edge in the graph. So you have this implicit representation, which means you don't physically have the graph, but you can, on the fly, do graph operations by using the natural operations in whatever object you were given. So this is the main benefit to adjacency lists, is usually when you have something modeling pairs, You probably have a pair operation, and it's all you really need to use to do graph stuff, is to be able to check is this a pair or not. So that's the main benefit. And he goes into some detail about implicit representations, so if you want more details, it's there. But that's generally what we're going to do is, in most homework problems and stuff, you're not given a graph that's too easy. It's some weird like dogs and cats and the relationship is if they can eat the same food or not. Or you have like genomes and it's the cell interactions that are the pairs. And naturally you don't want to make a graph for that. You just want to discuss those operations. So you could say like the protein interactions. So in your homework you wouldn't say there's an edge, you'd say, oh, this protein interaction or something. Or if you want, you could convert it into a graph. But you don't have to for adjacency lists. And that's the benefit. Okay. So that's all the background stuff. So now we're going to do actual stuff. So any questions on all those definitions? You don't have to have memorized all of them, but just when I explained it, it wasn't super confusing. That's good enough. You can always reference those definitions in the book again. So, okay, depth first search. What's depth first search? A recursive way to search a graph. So it's very natural. So the first thing, I'm not going to motivate this, but you need a marking mechanism just so you don't end up getting an infinite loop when you're doing this. So the first thing you want to do, if V is not marked, mark V. This makes sure we don't revisit the same vertex many times when we're walking through our graph. And I guess I should mention, we're trying to solve the reachability problem. So you have a node S and you have a node T, and you want to figure out, is there a path from S to T? So like usual with recursive algorithms, we're looking at the middle of the process. We're not at S, we're not at T, we're just at some node V. V could be anything in the middle. So for picture's sake, we've taken some steps already and we're at some V, and then we want to build the rest of the path to T. Or find that there isn't one. So if V is not marked, we mark V, and then for every edge, V to U, we're going to mark U, and then recurse on U. So in particular, U might already be marked, so let's also take that into account, just for efficiency. Mark U, DFS on U. And this is the whole algorithm. So at the end, what you're going to do is call DFS on S, and then check is T marked. Okay, so you've probably seen DFS before, but now let's think about it through our recursive lens. So immediately, we check if V is marked, so have we visited V yet? If we have not, then we're going to go to V. So the key defining feature of DFS is it says if we can move, move immediately. We just go there right now. We're not going to do it later. We do it now. So we move to V immediately. So we're at V, and now we have to figure out a next move. So these are all our possible next moves. And then for each possible next move, the DFS is really asking the recursion fairy, can we get from U to T? Because V to U plus the path from U to T gives you a path from V to T. And this just follows because you can recursively define walks. A walk is the last edge and another walk combined together. Or a walk is the first edge and the rest of the walk. So you can recursively define walks. So first edge, S to V, followed by a walk, or a walk is the empty walk. So that could be just a single vertex, for example. Or it could be literally no nodes. It's just empty. So that's how you can define a walk. It's a first edge followed by a walk, or it's just, there's no edges. It's just a single vertex or nothing. Or you could flip it and say it's a walk followed by a last edge. They're both the same thing. Either one's fine. And you'll use each one depending on the context. So here we're using the definition where we have a first edge and then the rest. And so why is the algorithm correct? Well, any walk from V to T has a first edge, or V is equal to T. So that's basically the induction proof. So our induction proof is either V equals T, and then we're done. There's a walk from V to T, being the empty one, or there exists a first edge. And we tried them all. There's also the last case where there is no walk, in which case we'll also be correct because we'll never hit T then. But those are the two main things. So DFS before, you might not have thought of it this way, but really you're just saying either we're at our destination or we're going to try all possible next moves, and then the recursion fairy will do the rest and take us to our destination. And if there is a way to get to our destination from our current location, then it must start with a first road. Okay? Any questions on this? So that's a quick proof of correctness. Here's the algorithm, and then what's the analysis? Well, for each node, in the worst case, we're going to call this on every node. That's the subproblems for every V. So we'll call this method for every V in the worst case. And for each V, how much work do we do? Well, we're going to loop through all the neighbors of V. And for each V, we do degree of V work to consider each neighbor. Okay? So in total, what's the running time? It's the sum of all V of the degree of V. There's technically a +1 too, because we do some constant work on V itself. And does this look familiar? I think it does. It's O of V plus E. And now to even describe the graph, we need to describe all the vertices and edges. And so this is linear time in the representation. So here's an important thing about algorithms, is you're always talking about the running time in terms of the input size. Up to this point, we've almost exclusively been looking at array problems or matrix problems where there's like a nice n parameter, and m is telling you everything you need to know about the running time and the input size. But here, and for algorithms in general, you might not just have a single n. You might have multiple things involved with the input size, and so you have to analyze your algorithm with respect to all of them. So for this algorithm specifically, if the edges were really small, there's not a lot of edges, then this is O of v time, which is really fast. But if there's a lot of edges, the edge size can be almost v squared because you have all the pairs of nodes, and so it can be very slow. But we don't really care if E is big or not. We just care that E is the input size. It's linear in the input size, even though it could be quadratic in the vertex size. So this could be O of v squared if E is large, but that's still linear. Because the input size is v plus E, which is O of v squared. Okay? So just to clarify, these parameters we're looking at, even though they might be quadratic or larger, it could still be a linear method because linear is with respect to the input size, not necessarily to these parameters. These are just things that are associated with the input size. It's not the same as the input size. Whereas for arrays, the input size and n are literally the same. Here, that's not true. N is usually just the number of nodes. That's what we use n to mean. Okay, so that's something I just want to throw out real quick. This won't be really important until like the end of class, but I just wanted to mention it. So any questions on DFS? Okay, so now we're going to do harder DFS. It's called whatever for search. So this is just a generalization of DFS. So this is going to generalize DFS. And the idea here is we don't really care what the specific data structure we're using to store things. So if you've seen DFS before, another way to represent DFS is to do something like this with a stack. So instead of recursion, you just keep putting nodes onto a stack and then popping them off. But we don't really need to use a stack. We just need any data structure that allows you to store things. So a general way to search a graph is you have a big bag of nodes. And at each point in time, you're going to take a node from the bag, and then you're going to do this process. You check if it's unmarked. If so, you mark it. And then you loop through all of its edges. And if you find anything that hasn't been marked yet, you're going to put it into the bag to be processed later. Now for DFS, we don't process it later. We process it now. So the whole point of DFS is if you have the chance to visit a new node, so if you're at V, and you can go to W, you're going to do it. So you move now for DFS. But for other algorithms, maybe you don't want to move immediately. You're going to delay it for whatever reason. And depending on what this bag is, that will determine the order that you visit all the nodes. But that doesn't change the correctness. So still, our proof by induction is still true here. It's just slightly differently how we prove it. So here's the claim. So the key claim here is the top one. You don't have to worry too much about the second one yet. So anything that we can reach from S, we will mark. That's the key thing. So we no longer have induction in the straightforward way of just, oh, we had the recursion fairy do the rest. Now we have to do something a little more clever. So how are we going to do this? Well, let's do it by induction. On the length of a shortest S to V path. So this is going to be similar to the walk argument we did before. So before we just did induction on the recursive algorithm, now we're doing induction on the length of paths. The proofs are going to be basically the same, but notice we're doing induction in different ways. The induction this time will be harder. So that's why recursive algorithms are awesome, because the induction hypothesis is kind of built in, right? You don't have to think about an induction hypothesis, because it's always the recursion fairy does the rest of the work correctly. Here we have to actually think about it. So the first thing we do is we put S into the bag, which means we'll immediately take S out of the bag and mark it. So the base case, S is marked because it's put in bag, then taken out immediately. How do I know it's taken out immediately? It's the only thing in the bag. Okay? So that's correct. We marked S, and I'm pretty sure S can reach S, so that's good. So what's the inductive step? Well, we're inducting on the length of a shortest path. So we want to somehow use that to our advantage. So let's take a shortest path from S to V. There could be many of the same length, but let's just pick one. Now, how do we define a shortest path? Well, it's a walk or a path from S to U, and then an edge from U to V. I'm drawing it with arrows here just to clarify, but this is an undirected graph. So really it's just U to V. There's no direction, but just for illustration, I'm putting the arrow there. Okay, so we have some S to U path, and then a U to V edge, right? That's what makes up an S to V path. In the case where S is not equal to V. So if S is equal to V, well, that's taken care of in the base case. We always mark S. Okay, well, what do we know? Well, this S to U path right here, it's got to have shorter length than the S to V path. Why is that? What's the length of the S to V path? Yeah, so we have one edge for S or for U to V plus the length of the S to U path. So naturally, 1 plus something is going to be bigger than the something. So this is smaller. This thing is smaller than the length of S to V. And so the induction hypothesis implies that U is marked. Right? So the induction hypothesis here is anything reachable from S is marked by the algorithm. So any U reachable from S in under length of S to V steps is marked by whatever first search. That's our induction hypothesis. So we know U is marked. So let's think about what happens when U is eventually taken off the bag. So because U is marked, we know it's put into the bag. That's the only way to mark it, right? We mark it and then we put things in the bag. Or if it's marked, it was already taken from the bag, technically. Either way, we know it was in the bag. And so we take U from the bag. So V equals U right now. And at the first time U is marked, we loop through its edges. So because we know U is eventually marked, we know this loop at some point must have executed this command, because that's literally the only way to get marked, unless it was already S. Okay, so we marked U. Now immediately after we mark U, we put all of its neighbors in the bag. What's one of the neighbors of U? V. So remember, UV is an edge. And so this line right here will put V in the bag. Okay? So we know we put V in the bag eventually, specifically right as we mark U. And now because our bag is finite, eventually we're going to take V from the bag. So each time we're only looking at unmarked vertices. So eventually everything else in the graph will be marked except for V. So eventually we have to take V from the bag, at which point we know it's unmarked and so we mark it. So that's the proof. So U is unmarked, and then V put in the bag when U marked. So V taken from the bag eventually and marked at that point. Okay? And notice this is actually an if and only if. If something's not reachable from S, we will not mark it. And why is that? Because if it's not reachable, there's no path, there's no sequence of edges to follow to get there. And so if our procedure just follows sequences of edges, well, we definitely can't get there. So it's actually an if and only if. Any questions on that? Okay. So what's the running time of this algorithm? So before, we didn't have this overhead, but now we do. So let's say taking V from the bag and putting V in the bag costs T for some T. Okay, so this costs T. So every node is going to be put into the bag and taken out of the bag at most one time. So the very first time we visit it, we put it in the bag, then we take it out of the bag, and then we mark it. Okay. So in total, we can think of this as summing again over all vertices. So for every vertex, we're going to do this procedure. So we're going to do one work to like mark V and stuff. And then for each degree, each outgoing edge, we have to put W into the bag. So we're going to do T work to put everything, all the neighbors into the bag. So this is what it looks like. So we have an additional overhead because we're not doing DFS here. So overall, this is O of V plus E times T. Right, again, we move the summation inside. So that's going to be, this becomes a sum of E, and then they're just all scaled by T. So depending on how we implement the bag, this could be really fast or it could be really slow. And we'll get different behaviors. So just an example of how you can generalize these procedures and accomplish different things. Yes? 1 plus is just because we're doing, like we're marking V, we have to grab V. There's just some operations we're doing on V itself.
And that doesn't cost T.
Nope. I'm including the T as the point when we're putting things in the bag.
Taking out doesn't.
Yeah, taking out also costs T. So, so when you're taking V, so I'm modeling this slightly differently. So I'm saying we're taking V out only when we hit an edge, right? So this won't be true for every vertex because some vertices aren't reached. we only take things from the bag if we followed an edge to get there. So I'm associating the cost of the bags with the edges followed. So you can think of each edge as being directed. So when we put something in the bag, I'm charging this edge, 1. Think of it as charging the tail of the edge. And then when we take it out, I'm charging the head of the edge. So I'm putting the cost for all the bag operations on the edges instead. So I'm just using associativity or commutativity of summations to do this. So you could attribute it to the V part, but you're going to get a different running time that's not as clear what's going on. So I'm just like manipulating the terms in the running time to get like a nice output.
So the T is just associated to the connecting
Yeah,
vertexes.
right. It won't necessarily be every vertex, unless we repeat the process on every vertex, which usually you want to do. So the running time is O of V plus E times T. So if you use a stack or a queue, it'll be O of V plus E. Because for a stack, you can push and pop, constant time. For a queue, you can add something to the queue, take it off, constant time. And so you can get different algorithms depending on the bag that are still linear time. They're just as fast as DFS. But you can also use a priority queue. And then it's O of V plus E log V. So this one's going to be slower. But the benefit is the priority queue allows you to compute other stuff. So now you're not just computing paths, you're computing like shortest paths, longest paths, some kind of weighted path in your graph. And we'll talk more about that later, but for now I just want to point out, you can use more complicated data structures and get a slower runtime. So in particular, if you use a stack, you get a depth first search. If you use a queue, you get a breadth first search. And the way the algorithm actually operates will look like this. So for depth first, you're going to start in the middle. That's our S. And you're going to keep making a move. And every time you can make a move, you just do it. So you're just going to keep following the spiral. And then you've hit every node. You're done. For breadth first, you're not going to do that. You take one step, you come back, take another step, come back, take one step, come back, one step, come back. Then you take another step, come back, etc. And it's going to grow this tree outward, just like that. And overall, when you're doing this process, you're creating a spanning tree of your component. So for the component that has S in it, you're going to hit an edge for each node in the graph. And so it's going to be a tree. There's no cycles, right? So because you're marking the vertices, you're going to break cycles. If there was a cycle, we'd hit an infinite loop. So that's why we mark vertices. And so there's no cycles, and we know every node in the component is hit by our proof up here. That's what that says. So if every single node is touched, we always follow edges to touch the nodes, and we don't generate cycles, well, that's exactly the definition of a spanning tree. So notice all of these variations of whatever for search are actually building spanning trees. So if you don't just want to know whether something is reachable or not, you want to know more about the structure of how to reach it, these algorithms will do that for you built in. They actually solve the more general problem of computing spanning trees for components. Okay. And visually, you can see these are trees. Like, there's no cycles, and we hit all of them. And that's the second part of the proof. The second part says these are all spanning trees. I'm just skipping that, but you can read it in the book. So any questions on this? So this algorithm that originally seemed really, it's not doing much, right? Like you could search the graph by just checking the adjacency list. Just search the nodes. But what's cool about this is it's doing other stuff. Depending on how you pick the bag, you can get different algorithms and different spanning trees. And they all have really interesting properties that are very useful. Okay? And notice this is kind of a reduction, right? So this bag operation, we're not building the bag. We don't know anything about the bag. We're just using the bag to perform this procedure. If the bag doesn't work correctly, our algorithm doesn't work correctly. So we are using the bag to solve our problem. And so the bag algorithms, like taking from the bag and putting into the bag, we're really reducing to the bag operations. So this is an example of a reduction as well. So any questions on this? Whatever first search. Yes?
I feel like I'm understanding like every step that you're explaining.
Mm-hmm.
I'm not sure if I'm understanding like what it's actually doing.
What the algorithm's doing?
Yes. Well, like, I'm not exactly getting like once you take V from the bag, and it's marked like how is it used to like create a path or a relationship?
So the marking is only so that we don't visit the same node multiple times. So the marking says this is a new node, we haven't been here before. So if we haven't been here before, you can think of physically we're walking on the node now. So we're physically here. And now we need to move further. So what the bag's saying is for every edge leaving V, we're going to put these on the bag to be visited later. So each of these gets put on the bag, or put in the bag. And then depending on how the bag is structured, maybe we'll visit these immediately. So for DFS, if the bag's a stack, the very next node we take from the stack will be U. We'll immediately visit it and continue. If the bag is something like a priority queue, maybe these are low priority, so we're not going to visit them for a very long time. We're just going to delay visiting those till the future. But the point is we're storing them, and so eventually we will visit them when they come out of the bag. And we only visit a node if we've followed an edge to get there. And since we keep following edges, we are building a path. And so that's how we know that there's a path from S to one of these nodes, because we're keeping a path built the whole time.
So basically, this is just like a structure of like whatever like algorithm could be, and then I specify what the bag is and like how to store it and change it to.
Right. So the whole thing is how to walk on the path on the graph to visit all the nodes. And depending on the bag, you're choosing an order that you want to visit them all in, just like in this example. So depending on what your bag is, you get completely different orders that you visit all the nodes. Any other questions? Yes.
So, as for like both graphs, you don't reach to the same outcome, I would say, you cover all the nodes?
Yeah, so this is the same graph. The order we search in and the output spanning tree are different. So we're still going to hit every node, but the order we're walking in changes. So you could think of this as you're in a video game and you need to go to every location to win the game. Well, there's two different strategies you could use. You could just directly follow this spiral to visit them all, or you could visit one, come back, visit one, come back, and then eventually visit the next one, come back, etc. It's just two different orders you could go in. So you could think of this as you're a risk taker. So every time you beat one level, you go to a harder level and a harder level, and you keep doing that. Whereas this one is you beat all of the easy levels first, then you beat all the medium levels first, and so on. But in either case, you're going to beat all of them, just a different approach. So the bag could model risk averseness if you were doing some kind of graph search in a video game or in a maze. So there's lots of options here. It's a very general technique. Okay, other questions before we're done with chapter 5? So that was basically all of chapter 5. Okay, now it's going to be hard. So now we've been looking at undirected graphs. We're going to take a break from undirected graphs. We're going to look at directed graphs. In particular, we're going to look at directed acyclic graphs. So no cycles. Now for each directed acyclic graph, there's two ideas called sources and sinks. A source is any node that has no incoming edges, and a sink is any node with no outgoing edges. So you could think of it as the start and the end of the graph, kind of. You start at a source, you leave the source, you eventually end up in a sink. Once you're in the sink, you can't leave. There's no outgoing edges. You're stuck. So you start here, you get stuck here. Okay? So the key thing here is what's a topological sort? What's a topological ordering? So it's just an ordering of your nodes. So you're lining up your nodes in a sequence with the property that U comes before V in the order if U to V is an edge. So that's the formal definition. Visually, what this means, all the edges go from left to right. So if you line up all your nodes in a topological order, the edges all move from left to right. You will never have an edge that goes backwards. If you had an edge that went backwards, that's a cycle. But we're assuming it's a DAG, so there's no cycles. Okay, so any questions on what a topological sort is? Yes?
A tree is a dead, right? But,
A directed tree is, yeah.
okay. But not all deads are trees. Because these
So
directed acyclic graphs, right?
trees only apply, tree is an undirected graph concept. So it's kind of, you can think of it like that. So if you took a DAG, so the issue is if you had a DAG and you undirected it, it could have cycles. So a DAG isn't really a tree. They're kind of separate ideas. So,
Tree is directed, right? They have a parent-child relationship. That's like
not necessarily. So you're thinking of rooted trees. So a tree is just any connected acyclic graph. So for example, this is a tree. There's no real parent anything. It's just, but you could pick a root. So maybe you make this the root, and then it looks like this. So you can make it directed, but you can't do the opposite. You can't take a DAG and make it into a tree necessarily. Because, for example, that's a valid DAG. But if you made it undirected, now that's a cycle. Yes? Yep. Yeah, rooted tree, like a directed rooted tree is a DAG, yeah. DAGs are like a generalization of trees to directed graphs. Yeah, you can think of it like that for sure. So any questions about the order? Is it clear? You want to line up the nodes so that all the edges go from left and right on your line. Now actually computing this, it's actually not so hard. So here's the key. This is basically the algorithm. So if you take any post-ordering, such as, say, a DFS, DFS computes a post-ordering because children are evaluated before parents. If you take a post-ordering and you reverse it, you get a topological order. So if you did like a reverse DFS, that's topological order. But for us, we're going to care about reverse topological order. So a reverse topological order is a post-ordering. So why do we care about this? So this is the opposite of what we want. So typically, if we think of like a dependency graph or recursive algorithms, we want to evaluate a node after everything it depends on is done. So a topological order is the opposite. It says evaluate this before everything it depends on is done. So we don't want that. We kind of want to flip it the other way. So the thing we care about is reverse topological orders, usually. And so you can do that with a post-ordering, such as a DFS. So the takeaway here is you can always compute this reverse topological ordering just by using a simple DFS. It's not as complicated as it seems. In particular, you can compute it in linear time, either explicitly or implicitly. So you don't actually have to save the order to like an array. On the fly, you can figure out what should go before what by just following the DFS tree. So you don't actually have to save anything in memory to compute this. You can do it on the fly. And we've done this before. And here's the big, this is like the final thing about DP. Every single DP algorithm is equivalent to a post-order traversal of the dependency graph of its recurrence. Like all of them. So every time you do TP, what you're really doing is you're building this dependency graph, and then you're running a DFS on it. That's it. So if you're someone who really loves graph theory or visual type problems, you can always think about DP as you're building this dependency graph and you're evaluating the subproblems in DFS order. So for example, this subproblem, maybe it's problem ij, because this is edit distance. Actually, so this would be mn to be precise. So what this does is you're running a DFS. Once you get to that node, you're building its solution based off of these subproblems right here. And the base case is up here. So that's the base case. So you're doing a DFS. You're starting with that top row. The top row is where you're actually computing stuff at the beginning. And then you're propagating the answers up throughout this graph in a depth first search order. It's pretty crazy. So an optimal sequence of decisions, remember, like in edit distance, we have to decide, are we going to insert, delete, or substitute a character. That sequence of decisions we're making is equivalent to just following an optimal path in this DAG. So maybe this is the optimal path in the DAG, and that's equivalent to the sequence of decisions that generated that path. So this would be something like, that's a substitute, that's an insertion, that's an insertion, that's a substitute, substitute, and then a deletion. So this is an exact equivalence between the sequence of decisions you're trying to compute in DP algorithms and this optimal path you generate through the DFS. Okay? There's just one exception, which is tree-shaped DP. So whenever you're doing DP on a tree, this isn't really true. It's not a path anymore. So for a maximum independent set, that's not a path. You're creating an actual set. So it's slightly different for those types of problems. But what's cool for those types of problems is the dependency graph is your DAG. So when you're doing dynamic programming on a DAG, the dependency graph is exactly your input graph. They're the same graph, which we'll see an example of in a second. But any questions on this high-level idea? Every time you're doing DP, you're really implicitly, you don't actually build the graph, but implicitly, you're creating this graph and following it in a depth-first search order. You build the subproblems, solutions, and then you propagate them forward to their parents. Yes?
Is that the full dependency graph, or is that the deduplicated states?
This is the full dependency graph. So remember, dependency graphs don't take into account that recursion might call the same thing multiple times. It's just the subproblems. And that's just because in dynamic programming, you won't call things over and over. You're going to memorize. Okay? So shortest paths, yes.
Is that kind of like backtracking? Like, what's the difference between that?
Remember, backtracking, we might repeat the same problem multiple times. Otherwise, there's no difference. So dependency graph just says what subproblems do we depend on. That's all. It could be true for backtracking algorithms. It could be true for DP. The only difference is usually DP graphs are going to be smaller because there's no repetition. Okay. So single source shortest paths, we're going to talk about this a lot, but I just want to start with a single example. So let's think of computing the shortest path from a source S to every node in the graph. So I already wrote that here. So we have this source vertex, and we're basically creating a distance function, or you could represent it as like a distance list, d of v, where d of v stores the length of the shortest path from S to v. So you're not just doing it for a single S and T, you're doing it for every single v. You want to know all those shortest paths. Now you're probably wondering, why do we need all these shortest paths? The answer is because to compute the shortest path from S to any specific T, it's actually necessary to compute all of them. So actually solving the more general problem, again, is useful for solving the easier problem, which is a general pattern in algorithms. Okay, so that's what we want to solve. We're going to do it with dynamic programming. So we already have our subproblem. D of v is the subproblem. So how can we compute D of v? Let's start with the easy case. Can you tell me the distance from S to a specific node right now? To any node? Yes, so the distance from S to S is 0. So v equals S. Okay, otherwise, what's a path from S to V? Okay, I heard some things. So remember, we can break any S to V path into an S to U path, and then the edge U to V. So that's going to build our recurrence relation. So the question is, which U do we pick? What U do we put in there? I heard it. Someone say it louder. There's another answer. I heard it again. Try them all. We're going to try all the u, okay? So we're going to take the minimum over all u that have an edge to v of the weight of the edge u to v. So it doesn't have to be 1 plus. We can assume it's a weighted graph. We can solve the even more general problem. So the weight of the path is the weight of the last edge plus the weight of all the other edges. So it's plus the distance to u. So if we're already at S, we know the answer is 0. We do nothing. Otherwise, we're going to try all possible last steps to get into V. And we look at the weight of that last step plus the weight of all the previous steps recursively. So the recursion fairy is going to give us this. And then that distance plus that weight gives us the distance for the whole path. And then once we have the distance for the whole path, well, we just pick the best path. So this just picks the best path. Okay? So usually we say, okay, return this for d of t or something. We're not going to do that here, but you could. So if you wanted to, you could return d of t. You could do that if you just cared about t. But for this problem, we're returning the entire list. So we're going to generate a list d, and that's what we return. So d is an array where d of, let me put brackets, the array d is going to equal the distance of the distance function. Okay? So any questions about the recurrence? Why this recursive formulation works? So it just follows from this recursive definition of a path, right? The weight of a path is the weight of its last edge plus the weight of the other edges. What are the other edges? We don't care. That's the recursion fairy's problem. Yes?
Are we given that such a path exists?
That's a good question. Path exists. So if you're looking at a specific node t, no, it doesn't have to exist. But this is computing the distance list for all of these v's. So after you compute this, for any of these that are undefined, you could just make them infinity if you wanted. But for simplicity, we can just assume S can reach all of the other nodes. So just assume that. Okay, any other questions? Yes?
Oh, would you want to explain the last line as like return the from 1 to n and then the array equals the distance of v?
Yep, so I'm just saying we're saving all the function definitions of v into an array. So we're going to compute all of these and then save them to an array.
So why don't we call like backtrack? I don't get it.
Why it's not backtracking?
Yeah, I feel like it's very similar concept as
Yeah, because DP is backtracking, right? So the algorithms are always backtracking algorithms. We're just memoizing them. We're saving subproblems so we don't repeat the same work over and over. Yeah, don't worry about the words backtracking and DP. They're all the same thing. What's important is you have a recursive definition of your problem you're trying to solve, and then you save them to some data structure. So this is just the recursive part. We have to do all the other DP parts, right? So what are the dependencies? This one's easy. The dependency graph is the graph. So any node, V, depends on everything that comes before it in the graph. And so if you drew the evaluation, the dependency graph equals G. So you have V, it depends on all of its predecessors. They're exactly the same. So if we wanted to pick an evaluation order, we need to make sure if U comes before V in the order, then U, or I guess let me rephrase this. If V is in the order at some point, everything that have edges going into it have to be present first. So what does that sound like? So to compute V, need all U with U going to V. What kind of ordering is that? I'll give you a hint. It's either topological or it's reverse topological. Yeah, just topological. So if U has an edge to V, then U needs to come before V in the order. So what's our evaluation order? Any topological ordering. Any of them. Doesn't matter, we don't care. So the dependency graph is the graph, and the evaluation order is going to be a topological order. So we do a topological order, and inside, we just slap in our recurrence. You don't need to know what tense means. That's for future discussion. But this is exactly the recurrence right here. This part. It just says if we found a better path, where the path is the last edge plus the distance to that node, then we update our best path estimate so far. It's literally just the recurrence, just slapped in a for loop defined by a topological order. Now, if you prefer, you don't have to literally do a topological order. You can simulate a topological order by doing a reverse DFS. So you could also do this recursively in a DFS fashion, kind of like what we did for tree recursion. So if you recall from chapter 3, for maximum independent set, we did a DFS and then just saved something in every node and propagated those up. So you could either do it that way, or you could do it this way and make it a literal for loop. Either one, they're equivalent. Now the key thing here, the reason we can do this is because it's a DAG. If there was a cycle anywhere, if there was a cycle in our graph, there's a cycle in our dependency graph, and so we will infinitely loop when we're doing this process. Because if you remember the topological ordering stuff, there's a cycle, then in our order, we need to compute F to compute O, and vice versa. So we're just going to keep trying to compute F, which we'll call O, O needs F, and so on. And it'll just keep repeating infinitely. So another important part about recursion trees in general, for any recursive algorithm recursion trees are trees. They don't have loops. And similarly, for DAG problems, you also can't have directed loops for the same reasons, to avoid infinite loops. Okay? Now, what's the running time? Well, for each V, we look at all the neighbors. So if we just do the sum of V, of the degree of V, 1 plus, we'll get O of V plus E, which is pretty standard. So normally for dynamic programming on DAGs, you're going to get linear time. You have to do something pretty crazy to get something more than linear time, and we'll do that crazy thing next time. So that's pretty much it for today. The main takeaways here are for dynamic programming, you can always model dynamic programming as DFSing the dependency graphs. They are equivalent. So that's a general unifying framework for doing all of DFS, or all of DP. Yes?
When you first said that, you mentioned except for in some tree.
So that's just specifically for paths. So it's always true that DP is a DFS on the dependency graph. It's just not always true that it's an optimal path. It could be like an optimal arbitrary subgraph. But it is true that the DFS is equivalent. That's always true. And also, yeah, the midterms Monday during class. So, yes.
Are we still having homework next week then too?
I haven't decided for next week. I don't know. If there's some like a couple, like if I do, it'll be just 2 problems or something. I'm not sure yet. We'll see. We'll see how the exam goes. So I'll put a Piazza announcement later with all of the logistics on the exam. If you have suggestions, let me know. We can tweak it. And I might do a review over Zoom like Friday. I don't know yet. I'll see if anyone cares for that.